Good afternoon, everyone.
Good afternoon.
Uh, I welcome, first of all, I welcome our today's speaker, Dr. Rachayya Arakerimath, and also I welcome all the participants. Now, first of all, I will introduce our today's speaker. Our today's lecture is on the topic intelligent optimization tool in rapid prototyping process. And our today's speaker is Dr. Rachayya Arakerimath. He is the professor and head of the mechanical department at Raisoni College of Engineering and Management, Wagholi, Pune. He has completed his PhD in mechanical from Vishwesvaraya Technical University, Belgium in 2009. He has vast experience of 24 years in teaching and 1 year in industrial experience. He has published the large number of papers. He has published 73 papers in international journal and 2 papers in national journal. Also, he has published 21 international conference paper and 22 national conference papers. Also, he has organized 7 FDP and 2 STTP during his career. Also, he has received the grant of 8 lakh by the BCUD for the research work. He has completed the total 25 projects under his guidance, and the one one PhD students has completed the PhD under his guidance, and 8 students are pursuing their PhD. Also, he has published the 3 books, and he has 2 patents on his name, and he has received the 3 awards. So with this vast experience, I hope you will get very good knowledge on the topic for the today's. So I would like to welcome Dr. Acharya Arakerimath to deliver a today's session. Thank you, sir, for your kind presence over here. I would like to hand over the session to you.
Thank you, Kudre sir. You have introduced me to the audience. So I will share my PPT and then I will start my presentation. Right, sir?
Yes, sir.
Okay.
Sure.
Okay. So all right. So my presentation is okay now. Can you see, all of you?
Yes, sir.
Yes, sir. Yes, it's visible.
Hello.
Yes, it's visible, sir.
Okay.
Go ahead.
Okay. Okay. Good afternoon to all.
Good
I am
afternoon.
I am Dr. Rachayya Arakerimath. I have been introduced by Kudre sir. So it's really a pleasure to me to share my experience in the area of optimization with reference to the rapid prototyping or 3D printing. So here we all know that what is the rapid prototyping. See, this is the just the additive manufacturing process. So which is a constructive machining operation you can call. Basically, there are 2 types of the manufacturing technologies. One is subtractive and another one is additive. So based on that, especially the Department of Mechanical Engineering from Guru Govind Singh College of Engineering and Research, they have chosen a very rather good topic as far as the all mechanical engineers are concerned. So this is the advanced manufacturing process you can call. So here basically it is the the development in CAD CAM and the manufacturing automation you can call. So here basically what we do is we manufacture number of components maybe of different materials by layer by using the various additive manufacturing technologies or additive manufacturing processes. So this is really you can call this as a 3D printing technology, and where you can one can become a key technologist in the manufacturing engineering, and this technology enables complex geometric or organized shape of the parts to be designed and manufactured layer by layer by using the 3D printer. So here some of the objectives along with the 3D printer is shown in this slide. So as far as your 3D printing is concerned, it is a additive manufacturing technology where you can manufacture not only the the plastic components, even you can go for the composite plastics as well. So today, the additive manufacturing technology, it can be produced, the components layer by layer. So you can just look at this slide, which explains how the components are manufactured. So basically, what we do is we all know that CAD these days we are all using the CAD. So we may use CATIA, we may use Pro E, Unigraphics, or even you can use the the software which is given by the 3D printer itself. So basically, what we need is we need a geometric model of the component, or you can say CAD model of the component, and that is to be rather converted into the suitable format, that is STL format or whatever it is, and that is to be sent to the or interface to the 3D printer, and then that 3D printer it will generate, or it will build the component layer by layer, that is slicing up the model into different layers. The computerized model is sliced into closely spaced parallel horizontal layers, you can call. So here there are two sketches, one the 3D model which exactly manufactured, and then other side it is the 2D view of that. So here basically there are different steps. So initially in my presentation, what I do is I will focus best little bit on the 3D printing, and then I will go to the what are the optimization techniques, and then how the 3D printing will help for the optimization, right? So this is the just one more rather slide which will explain about steps in 3D printing. See, whatever earlier steps, these are all just represented by this graphical way. So we need a CAD model, then that is to be converted into STL format, and then we'll have to go for the machine setup, and then we have to build the model, and then whatever the unwanted edges are there, we have to remove it, and then post process, and then we can go for the various application, manufacturing of the applications. So this is a small this is a machine, 3D printing machine, and these 3D printing machines are available in different categories based on the type of 3D printing. So they may be of liquid based, they may be solid based, they may be powder based 3D printers. So some of the components which are manufactured by using 3D printing technologies are they may make use of stereolithography, they may make use of loam, we can call, that is laminated object manufacturing, and the third process may be selective laser sintering, then fused deposition modeling, then you may go for solid ground curing, or you may go for inkjet technologies, or you can say 3D plotting or multi-jet machining. Okay, so these are the six the famous 3D printing technologies which are available in the market and in industry. And some of the components you can see here, you can manufacture, or you can build even simple components to the complex component. So here is the engine which which is assembled engine. See, this engine, it can also be manufactured by using multi-jet machining, and in addition to this, the another one is there which is very complex in shape. So as far as 3D printing is concerned, it is a very good technology and emerging technology as far as mechanical engineers are concerned. So look at here, some of the comparison as far as the above approaches or methods are concerned. So when it comes to stereolithography, so normally its size is 20 by 20 bed size, you can call. So, and then accordingly the inkjet inkjet size, then fused deposition printer size, and then selective laser size. So if somebody is interested to develop the 3D printing lab or 3D printing setup, he may make use of this table. So he may go for these varieties, that is what is the build tray size, then he may go for what is the system price range, then he may go for speed is another parameter to define your 3D printer. So accordingly, the different methodologies, one has average, poor, and then good. Okay, so based on that, you can rather select which type of technology you want in your 3D printer. So most of the 3D printer, they make use of either FDM or SLS. So then in addition to this, another parameter before you purchase, you can go for what is the accuracy. So then in addition to accuracy, you may go for what is the surface finish required, then strengths, and then what are the weaknesses of each technology. So based on that, you may go for the 3D printer or the RP machine. Then in addition to this, there are various applications of these technologies. So look, based on your application, you may go for the particular choice. In addition to this, the another parameter you can choose is material. So here SLA is used for acrylic materials. Then even you may go for ABS, you may go for polypropylene, you may go for flexible or elastomeric water resistance material. So this is the SLA application as far as material is concerned. Then inkjet based printers, they are used for polyester based plastics, investment casting wax. Then as far as FDM and SLS, these are the very famous printers. So FDM printer, it will use ABS material, even polycarbonate, then polyphenyl sulfone ester. So these are the materials which you can use in the FDM. Then in addition to this SLS has got variety of materials, that is nylon, you may go for aluminum, then carbon filled and other good strength materials. Then polystyrene, you can go for steel and stainless steels. You may go for bronze alloy, then cobalt and all. Okay, so this is a just overview of the what exactly the 3D printers and what technology they are using for the additive manufacturing. So in addition to this, because when you go for optimization, you must know little bit about the 3D printing technology and their processes, and thus their parameters which will affect the quality of the 3D printed objects. So looking into that, I am just explaining here. Then in addition to this, as far as characteristics of the rapid prototyping technologies are concerned, they may be liquid based, powder based and solid based, as I told in my earlier slide. So here, as far as liquid based is concerned, the SLA technology, stereolithography, it will make use of liquid. Then even solid based curing is also rather using this liquid. Then in addition to this FDM, then ballast. So here, whatever this liquid based is there, so this 3D printer, they make use of various layer creation techniques, and then page change type, and then materials. Okay, so it is a just very good slide which will explain what are the characteristics of the different printers or processes which will make use of solid based material or powder based or liquid based. So looking into that, you can go for your application. And in addition to this, these 3D printers, the most important commercial rapid prototype technologies, available in the market. Again, this is just simple slide which will explain various parameters as far as their approaches are concerned. SLA, maybe MJM, and SLS, FDM, and all. So again, same parameters you can have: speed, accuracy, surface finish, strength, and weaknesses. Based on that, you may go for the selection. All right. So now let me explain. What are the different parameters, 3D printing parameters used by the various researchers or maybe various manufacturers. So basically, you can look at here the laser. So if you are using laser beam operated 3D printers, so here you can see the parameters used are laser power, laser beam diameter, intensity distribution, then wavelength, then operating mode. These are the laser parameters. Then the different materials you can use is as far as material is concerned, you may go for the different parameters. That is, what is the material particle size and particle shape, what type of particle shape you are using, and alloying element. So looking into that, you can go for the these parameters as far as laser base is concerned. Then in addition to this, you can go for the the thermophysical properties such as conductivity, heat capacity, and temperature, melting temperature of the wire is concerned, or those powder is concerned. Then in addition to this, you may go for environment parameters such as protective gas use, ambient temperature, gas temperature, then again gas flow rate, and then the bed temperature you may have a parameters. So when it comes to the conducting the experiment on the any 3D printing process, so you may go for these types of parameters. And in addition to this, machine is concerned, you may go for what is the packing density, and then heating, position, repeatability, then powder density, then material surface. These are the some of the parameters which will be considered as far as machine is concerned. So this is the just category of various parameters which are used in the 3D printing. Then in addition to this, this is the just the diagram which will represent the different parameters as far as FDM is concerned. So here fuse deposition machining is concerned. Here you can look at here again same parameters are represented in a tree format. So what are the various concepts used? Then you may go for even the unprocessed material. You may go for that is FDM machine where model build temperature you may choose, or you may choose nozzle diameter, or you may choose multiple nozzles. Okay, today see, no doubt the single jet machining is very rather high speed working. But in addition to that, when it comes to the complex components, complex component manufacturing is concerned, we may go for the multi-jet 3D printers, where you may have different nozzles and then nozzle diameters, and accordingly your research approach may change for the complex geometry. Then in addition to this, you may go for environmental factors, then part building factors and working factors, and thus the part quality and mechanical properties can be decided based on these parameters. All right. In addition to these above parameters, the 3D printed components, they are also rather their accuracy is also dependent on the lay pattern. So when it comes to the lay pattern is concerned, see printing layers, they may be at different angles. So these layers in FDM has different types of angles. So each type is used for different types of loading. So one may be 0 angle 90 degree, then you may go for 45 to 45, then you may go for even 90 degree. So what is this exactly? The angle in which the layers are printed is called as raster angle. So raster angle is very important as far as the surface accuracy of the 3D printed component is concerned. The raster angle has a direct bearing on the resulting structure, and it plays a significant role in influencing the mechanical characteristics of the parts and strength of the parts. See, as far as you all know that when it comes to the conventional machining, especially the subtractive machining is concerned, we all know that how surface roughness is calculated or measured. Okay, see, smoother the surface, so you can say the surface accuracy is better, and thus the friction is less when it comes to the rolling elements are concerned or rotating elements are concerned. Therefore, whatever the surface quality depends on the what type of the lay pattern you are using and what is the raster angle is used. In addition to this, when it comes to the 3D printed components, so some of the in addition to layer angle or raster angle, you may go for these parameters also, which will affect the quality of the 3D printed component, that is density. See, scan speed has a significant effect on the density. Therefore, this you have to have a control on scan speed of the printer. Then in addition to this, at sufficiently low scan speeds, the relative density is almost independent of the layer thickness for the selected range of the layer thickness, and it is maximum of 99% of the relative density. So in addition to this, at higher scan speed, the values are a higher layer thickness results into less density. So you have to have this density as one of the parameter in your working. In addition to this, see, basically we are interested in surface finish. When it comes to the surface finish, the parts often require post-processing operations such as surface machining. Then even you may go for polishing and short pinning operation to attain the high strength and the final part surface finish. In addition to this, surface roughness is heavily dependent on laser process parameters. Okay, so in this surface finish is also one of the outcome of your the printed components. So it is very it matters a lot when it comes to the accurate parts are concerned. Then in addition to this residual stress, so due to localized heating, the complex thermal and phase transformation stresses are generated during the process. So in addition, frequent thermal expansion and contraction also takes place. Previously, which is solidified layers during the process, it generates considerable thermal stresses and stress gradients that can exceed the yield strength of the material. So you have to have a control on these residual stresses. See, residual stresses can lead to the part distortion, and they may initiate fracture, and thus it is unwanted and it has to be decreased. It may decrease the strength of the component produced in the 3D printing. Okay, so these are some of the the parameters which we have to keep in mind, and which I have already explained these defects. So now let me go to the little bit about what is optimization here. So when you see, as far as my topic is concerned, it is basically intelligent optimization processes used in 3D printing, or you can call rapid prototyping. So looking into that, I have to concentrate more on that side compared to the what is 3D printing and what are the technologies and all. I hope you know it is a 3-day FDP. So probably yesterday you must have rather learned to those the rapid prototyping technologies and all. So now let me go to the optimization here. So you all know that when it comes to the optimization, this is just it may be a see you take any it is a mathematical operation, or it is a optimization is a numerical method which gives to find out the best solution of the given problem. And this optimization, it may be maximization problem or it may be minimization problem based on the whatever the domain you are working. So maximizing or minimizing some function relative to the some set of the variables, or given choice of variables, you may go for the optimum solution. The function allows comparison of the different choices for determining which might be the best solution. Okay, so the common examples, you may go for minimum cost calculation, maximum profit calculation, or minimum error calculation, optimal design, optimal management. So this optimization has got a wide variety of applications. And in general, you all know that the optimization problems are classified into various types based on their applications or utility. So here they may be of gradient type or non-gradient based algorithms. And you all know that the gradient based optimization means here you require information about the objective function value and its derivatives with respect to design variable. Whereas non-gradient means they require only information about the objective function. Okay. In addition to this, when it comes to the non-gradient algorithm, generally they are used to solve unconstrained problems with either real or integer design variables, and generally they obtain a global solution. Then, in addition to this, some of the examples which are used are random search methods. You may go for even evolutionary algorithms. You may go for simulated annealing. You may go for the taboo search method. So these are the some of the optimization methodologies which are used in day-to-day life. Then when it comes to gradient-based optimization algorithm, so as I told, it is used to solve both constrained and unconstrained problems with real design variables, and they obtain a local optima solution, and they require information about objective function and gradients of the objective. Then some of the examples as far as gradient-based optimization algorithms are concerned, you all know that linear programming, quadratic programming, sequential quadratic programming. Even you may go for steepest descent problem. You may go for Powell's algorithm. So these are the some of the gradient-based algorithms. Then in its when it comes to the gradient-based optimization algorithm, so problem statement is written mathematically. X raised to q is equal to h raised to q minus 1 plus alpha q into s raised to q. So this is the just mathematical the expression of the gradient based optimization algorithm. You can refer any textbook for the details. Now these optimization techniques or tools, they are also classified into two types. One is single objective optimization, we can call SOO. And another category is multidisciplinary design optimization or multi-objective optimization, that is MOO. So in addition to the earlier classification, the optimization methods are also classified into SOO or MOO. So now here you all know that the all engineering problems, most of them are covered in this category, that is multidisciplinary design optimization, or you can call multi-objective optimization. So look at here how exactly it works. You take any type of optimization, it is an iterative process. So based on the whatever defined inputs and the expected output, it is a iterative process. So when it comes to multidisciplinary optimization, you all know that there are different domains are there. One is discipline A, discipline B, discipline C. But discipline A may be a maximization problem, discipline B may be a minimization problem, discipline C may be a minimization problem. But what I want is I want a optimum output from these all three domains. So based on that, what I do is I will I will convert them into a objective vector J1, J2, J3, Jz, and then I will couple them, and then I will apply the optimization algorithm, maybe numerical technique, or maybe heuristic techniques such as genetic algorithm or maybe simulated annealing, and then I will go for the optimum calculation of the design vectors and the output vectors. So this is what the multidisciplinary optimization, or you can say multi-objective optimization, which is used for various the processes or maybe manufacturing operations or maybe in 3D printing. All right. Now, in addition to this some more inputs, the design process is carried forward gradually, often making small loops in the process while working towards the final goal. So ultimately, you all know that you take any type of optimization problem. So optimum optimization, I told you, it may be a minimization problem or it may be a maximization problem. And so it may be with reference to a process, it may be with reference to a rather system. So here you will have a certain inputs, then there is a system, and then certain outputs. So ultimately, you have to make use of certain optimization technique, and then you have to work for the optimum solution. So in this diagram, we have design and then analysis. So design, so various activities in the design process. Then analysis is concerned, it is the engineering science or a mathematical activities which will evaluate the performance at that stage. Okay, so in general, you go to any of the rather optimization book or any of the optimization material, you will find these steps as far as your design optimization is concerned. So when it comes to the rapid prototyping, or you can say 3D printing, here 3D printing, it is just one machining operation, or you can say it is one manufacturing technology. So before manufacturing any component, it need to be designed. It need to be designed optimally by using your maybe any of the CAD software, and then any of the your CAE software. Okay. So it is, again, I told you, it is a iterative process or trial and error method. But based on the optimization technique, then you may go for minimization of the weight, maybe maximization of the strength. So that is what the
Hello.
hello, am I audible?
Yes, sir. Yes, sir.
Okay, okay. So when it comes to the design optimization, so here you all know it is a just general procedure. So when it comes to the general methodology is concerned, you identify whatever problem statement or whatever need you require, then go for the definition of that problem statement what you want to optimize. Then you have to go for detailed conceptualization of the whatever that problem you want to optimize. Then you may go for preliminary design and planning, maybe using preliminary CAD software or any process. Then you will just generate that model, and then you test that model, and then once it is tested, then you may go for the prototyping by using your maybe even you may go for 3D printing, or you may go for conventional machining, and then you may go for detailed design, and then you can repeat this process based on the whatever your requirement, whether weight is to be minimized or whether weight is to be rather added. So based on your requirement, so this process is repeated. All right. So in general, so it has got various steps. So when it comes to the design optimization, it has got around 8 to 9 steps. So you need to define them properly, and then you have to go for the optimization. Okay, so this is just repetition of the whatever that earlier. And I told you when it comes to the optimization, so today, because of these CAD softwares or CAE softwares, or even some of the optimization software, this process is very fast, and then you can make you need not bother about what type of algorithm you are going to develop or write. So straight away you may make use of some of the the available softwares, and then you can do this process. And then you only thing is intelligently how to use them, whether it is to be used for minimization problem, maximization problem, then how constraints are to be rather given, that is subjected to g of x or h of x. So these are the 3 steps, that is determine an initial design, which is it is one example, and then you have to go for the computer simulation. Then you have to see you have to give accuracy, or you can say convergence value. So until that convergence value is less than or equal to the whatever your permissible value, you have to repeat this step. So this is what the optimization process is. All right. Now, when it comes to the the 3D printing product optimization, or it may be any design optimization. So basically, it is divided into three types. One is structural optimization, then size optimization, then shape optimization. So look at here what exactly it is. See, when it comes to the structural optimization, it has over the past decades qualified as an important tool in the design process. The method can be grouped into topology, or it may be size and shape. So, and thus you may have topology optimization, or you may go for size optimization, or you may go for shape optimization. See, the objective of the optimization can be minimization of the stresses, weight, or even compliance for a given amount of the material and boundary conditions. So look at here. This is a very simple problem when it comes to the optimization explanation is concerned. So we'll have to minimize. You see here, we'll have to minimize. Minimize f of x subjected to g of x, maybe, and then h of x. Okay. So here you take any optimization problem. So it is a just simple cantilever beam where you have applied the boundary condition. That is, the one side is fixed and other side is applied with the load of P. So based on that, you can define, my deformation should be minimum, or my stresses should be, at the my stresses wherever load is applied, stresses should be minimum. So these, they are the outcome of the whatever your optimization is. So in addition to this, look at here. So earlier it was just simple cantilever beam. Now it is a stepped cantilever beam. So here, what will be the change? Change is only the, the size is. Earlier it was an informed size, now it is a stepped one. Okay, so that means in size optimization we are bothered about the area. Okay, so here you can see here the number of design variables you have to define, and then you are going to define the what is the maybe thickness, how much should be the thickness at different steps. So looking into, and then what should be the mass, and then compliance and mass, these becomes the constraints, and the design variable becomes thickness, which is the x value. So looking into this, you can go for the size optimization. Then similarly, you may go for shape optimization. So whether I should have a rectangular shape or whether I should have a curved shape. So typical curvature you can obtain based on this shape optimization. See, this is another example where shape optimization is a part of the field of the optimal control theory. The typical problem is to find a shape which is optimal, in that you can minimize a certain cost, and thus functionally you can verify whether it is within the boundary constraints or not. And so the some of the examples as far as your topology optimization, shape optimization, and size optimization are concerned, you can see some of various engineering components. There may be fillet problem, there may be hook problem, there may be arm problem, rocker arm. Okay, so in addition to this, when it comes to topology optimization, you all look at this example here. The topology optimization is a tool for finding a domain in which material is placed that optimizes a certain objective function which is subjected to a constraints. So in this way, it will use topology optimization to find out the optimal mass distribution of a heavy commercial vehicle carrying the housing with alumni having same stiffness and performance as that of the currently used cast iron. Okay, so look at here. When it comes to the topology optimization, you may replace X material by Y material, maintaining the its performance and stiffness equivalent. Okay, so this is just simple example as far as topology optimization concerned. Now look at this example. This is one of my the MTech student work, which is done using hyper mesh, and then he has used even LSDN also. So based on that, he has applied this optimization technique for the. This problem is we have to minimize the weight of the the differential carrier. So you all know that today all industries, they are working on the minimization of the weight and maximization of the strength with the optimum cost. See, cost is the very important factor when it comes to the optimization is concerned. See, ultimately, if you are manufacturing a chassis of the truck, so it has got the tons of weight. So if you minimize at least maybe around 100 kg, or even 50 kg, that itself is your achievement, because that much fuel consumption is saved throughout the life of the truck, right? So looking into that, this is one simple example which was taken by one of the MTech student under me. So here what he did is he modeled this differential carrier, and then for different materials. So, and then his objective was to he has to rather have a adequate strength and then adequate shape, but same time same he has to minimize the weight. So first one was the baseline design, which is red portion, and second was the optimized design. So initially it was it was of 30 kg, but after applying his optimization technique based on the his analysis, he reduced by 10 kg. So look at here, he applied again Taguchi method for this method. So he has used three parameters, that is one is wall thickness, another one is height of the carrier, and another one is flange width. So initially they were of different sizes. So wall thickness was 9 to 10, then height of the carrier was 160 to 161, then the flange width was 15 to 16 mm. So, but after optimization, he brought the optimum values as 9 mm thickness, then height of 159, then flange width of 15, and thus he could able to improve his design, and then the reduction of 32% of the weight. So 32% of the weight of the overall carrier means it pays a lot. Okay, so this is what the importance of this optimization is. And listen here, what is the role of 3D printing here? So once once you make this optimization, what you do is you manufacture it as a prototype, and then you just test the what will be the the surface quality, what will be the strength quality. So you can because 3D printing is a very quick manufacturing technology as far as your the industry is concerned. So you can make a prototype, and then you can just check what are the different characteristics of the the manufactured component, and then you prove whether it is rather it can be used optimally or not, and based on that you can take the decision and send it for the final manufacturing to the industry. All right, in addition to this there are small structural examples also. So you may go for even the deflection minimization or value minimization. So this design optimization of the cantilever. So look at here, I have initially I had one cantilever which is taking 1 bar, but with the little modification, with the less deflection, it is able to modify for 2 bar pressors. And in addition to this, 17 bar with the same area with the less deflection, but load bearing capacity is more. So this is what is the advantage of design optimization. All right, in addition to this, you may go for topology optimization, another example. So instead of going for the simple rectangular 16 by 10 bar cantilever bar, you may make the changes, and thus the material is, there is a saving in the material with the same application and with the same strength. All right, so you can see the comparative outcome of the whatever this design. See the last the first design, conventional design, which was of 1 bar, but it was having more than 2 mm deflection. But the modified one, which one is having about 0.5 mm displacement, maybe little costlier, but overall the strength is improved, and thus it can be utilized for the particular application. All right, now in addition to this, another case study done is that is rocker arm case study. So you all know that what is the rocker function of the rocker arm. So the objective here is to design the rocker arm of a different materials using maybe CAD software, and to carry out the finite element analysis on the design model using ANSYS. Thus, we obtain various values of the deformation and stresses by finite element results. So, taking better material out of those analyzed material, and then modified for the same CAD software for the optimization. Finally, the modified 3D printed rocker arm is developed for the application. So here rocker arms, you all know that. Then here we are going to rather explain about how it is to be analyzed for the different materials, keeping same strength. So this is one case study. So you can look at here. This is modeled in maybe CATIA or whatever it is, and then so you may go for before optimization. What exactly the rocker arm shape is, and then after optimization. Okay. So then what will be the reduction in the weight of the rocker arm? What is the improvement in the strength of the rocker arm? So you can just look at here. This is another material. So this is before modification and after modification. This is carbon steel, and where again you can see here before modification and after modification. So the results we obtained here is for three materials. That is, one is structural steel, then HMCF material, then carbon steel material. So based on this, you can see the total deformation, which is 0.015, 0.015, and 0.014, and equivalent stress is equally, you can see here. Whereas the maximum shear stress, then safety of factor of safety, then again weight. So looking into this, you can conclude that the percentage change in the weight you can see here, and then accordingly percentage change in the strength. So based on this, you can take the whether the optimized rocker arm it is usable for the particular application or not. So this is just one of the again project work or research work you can call. So accordingly, one can just play with the softwares and then manufacture on the 3D printer, and then you can work for the what is the weight, what is the strength. All right. So in general, this 3D printing technology, when it comes to the the different optimization technology is concerned, these are the steps here. So we may go for loading up the various maybe components after the design optimization, and then you may play with the different materials. Okay, as I explained earlier. So once you do the optimum design, then you may go for you may play with the material to increase the strength or to reduce the deformation, and then you based on those process parameters of your 3D printer, then you may go for its validation. So this 3D printing technology has led to the one more research development. In addition to this, here you can see another example. This is optimal design of the automotive lower arm for 3D printing. So initially you can see here the conventional the lower arm. So conventional lower arm, it was a fully solid, having end circular holes. But ultimately my aim, my function is to be fulfilled, but unnecessary weight has to be removed, keeping same strength constant. So that is what has improved in the last figure. And ultimately this testing, this manufacturing testing, it was done on the the 3D printing. Okay, so this is a very beautiful example as far as the lower arm optimization is concerned. Similarly, you may go for so this is one example, same continuation of the example. So conventional process versus 3D printed component of the automotive lower arm. So conventional process you can see here, and in 3D printing the same the 60% weight is reduced. And similarly, see, two aspects in saving materials in 3D printing are, one is in the design process, and second one is in the printing process. So for 3D printed redesign to save the more material, one is material saving and another one is you are going to rather maintain the same rather strength. Weight is reduced, its strength is maintained, and then the cost is reduced. So this is what the one more example. So same way, the process parameters, what are the process parameters and key point indicators or key point indicators used in the 3D printing process. So same earlier methodology we can see here, but only thing is we have to work out on what are the key performance indicators. See, ultimately, see, today we all are using the 3D printer, but ultimately what is the aim of the 3D printing, or what is the aim of the RP process is, I have to manufacture a high quality product with less production, with less production cycle time, with maximum accuracy, with minimum waste. So these are the four key performance indicators when it comes to the 3D printing is concerned or rapid prototyping is concerned. So keeping these key performance indicators in mind, we have to go for the our the optimization process. See, ultimately, some people may say that a optimization is a numerical method, it is only by the mathematicians. No, this optimization is its application of optimization, or application of optimizations are everywhere. You take any process or any system, you can use them, but ultimately the knowledge or that how to use that technology requires experience. So look at here the process parameters and key parameters, what as per as our 3D printing is concerned, same methodology whatever lower arm is is concerned. So this is just explained with figures. So similarly you can see here same, you can write that tree diagram as far as FDM process is concerned. Okay, so I told you in the earlier slides, the layer, whatever that layers are very important, whether cross layers are there or whether zigzag layers are there or whether circular layers are there. So those layers play very important role as far as your strength of the component is concerned, or the shape of the component is concerned. So looking into that, you can draw this cause and effect diagram before going for the optimization process is concerned. So when you come across FDM process, so this is the cause and effect diagram for optimum 3D printing process is concerned. So you may have concept models, maybe topology optimization. You may go for materials. So as far as materials are concerned, you may make use of melt and cool parameter, density parameter, and color parameter. Then in addition to the orientation is concerned, those orientation may be X direction, Y direction, and Z direction. Similarly, you may go for machine FDM machine parameter, and then you may go for the working parameters. So when it comes to the FDM working parameters are concerned, you may go for what is the counter width and gap, what is the raster width and gap, layer thickness. You may go for raster angle, layer angle. Then you may go for part interior style. So these are the some of the parameters which will affect the quality of the FDM process, and thus your optimization process inputs are defined. All right. So in addition to this, what are the effects of this print speed and layer thickness on the component covalence? So influence of print speed and layer thickness on covalence in FDM is concerned. You can look at here. So this covalence, it affects on the surface contact, surface texturing, and it also affects on neck growth. It also affects on the diffusion and the randomization. So the formation of the bonds in the FDM process is driven by the thermal energy of the semi-molten material. So looking into that, you can see the graph here. So print speed versus coalescence is concerned, as when the sprint, when print speed is less, so coalescence is little bit higher, and when print speed is increasing, then coalescence becomes rather lesser. So similarly, you can see for 0.5 mm thickness and again 1 mm thickness, layer thickness. Okay, so looking into that, you can widely, intelligently you can play with your parameters. All right. In addition to this, what is the effect of build orientation on tensile strength? See, ultimately, when it comes to the manufacturing process, tensile strength is very important. So here, this is one more case study, how which will explain the build orientation on tensile strength. So look at here. Again, you can see here the different graphs. So this blue indicate default 1, and then another one will indicate default 2, then red indicates optimal. Okay, so at the end you can see here, so optimal red one. So initially it was at higher side. So after playing with the strength of the injection molded component, so the the flat one is giving the optimal strength, or you can say maximum strength, right? So like this you can just play with the different parameters and then apply your optimization technique. Next, what are the various research areas as far as your 3D printing is concerned? Today, we all are rather, searching new research topics. But when it comes to the new research topic, what we do, we go for the conventional machining operations. So instead of going for the conventional machining operation, better, play with the new technologies like 3D printing. So there are more than 6-7 technologies are there in 3D printing. So you can just go through those 3D printing technologies, and then you make some new modification, or maybe some new, invention of the new material, which can be replaced by X component or Y component, so that itself will be your one of the the research area. So here you need to develop a models for predicting the key performance indices in terms of process parameters. Then optimization of the process parameters such as raster angle and gaps, then laser power, then scanning speed, then exposure time and point distance. In addition to this, you may go for thermal and chemical mechanical simulations of the material melting and cooling process studies. Then you may go for measurement of mechanical attributes for various process parameters. This is another area. And in addition to this, you may go for multi-scale approach to select the best process parameters. Then you may go for need to perform topology optimization considering material anisotropy and layer direction. And you may work for fiber reinforced composites and new materials. Okay, so today, the based on the development in the manufacturing technology, maybe micro manufacturing or nano manufacturing, so this fiber reinforced composites is another area which is developing as far as 3D printing is concerned. So in addition to this, you can see here the composites for 3D printing. So in addition to the conventional composites, you may go for metal matrix composites materials. You may go for plastics, nano composites. You may go for short fibers, long fibers, and continuous fibers for your research material. Then in addition to this, the resin reinforced with the chopped carbon fiber is placed layer by layer that can be applied for various that can replace the conventional material. Then temperature difference and cohesion between the individual beads and resulting in asymmetric shrinkage and bending moments can be studied. Okay, so when it comes to the 3D printing, ultimately you have to play with the process parameters. You have to play with the different composites for the different materials, and then you may develop a new material. All right. So some of the research papers which are published, you can see there is automation of selective laser sintering process parameters on surface quality. It was done by these authors. Then even you can go you may go through the elsewhere publications or Springer or AHME. So this is another. This is using the FDM process for the they used teaching learning based optimization algorithm. So when it comes to the your optimization process is concerned, there are n number of optimization algorithms are there. You may make use of them for the optimization of the objective functions. Okay, so this is all from my side. So I request maybe audience or faculty to my presentation is over now. If you have any doubts, you can ask me. And as far as optimization is concerned, I have some more slides, but that may take a little more time. So I will stop here as far as the overall, the use of the optimization in 3D printing is concerned. Yes, sir. Hello.
Huh. From audience, any doubt? You can free to ask to the sir.
If any doubts
I
are
think,
there,
at the start of presentation, some one of the student asked that about that angle.
okay,
That
raster angle, raster angle.
Yes. How to calculate and what is this?
The raster angle, it is layer angle. When it comes to the you can I will just go to that slide and I will show him. So the raster angle is one of the parameter which will consider the strength of that component. So look at here. So you can look at here. See, when it comes to the printing layer, so this is the raster angle. Here, parallel, when layer by layer is manufactured, so those layers, they may, which are developed, they may be of 0 degree, 90 degree, 45 degree, or maybe, they may be 90 also. Okay. So this angle is the angle in which the layers are printed in is called as raster angle. That's all. Yes, sir. Hello. Hello.
Yes, sir.
Ah.
Is there any more doubts?
All right. So if any questions even are there, you can send it on my mail also, and then we will interact. No problems.
Yes, sure, sir.
So I hope I took 1 hour. So I don't know whether my speed was okay or
Yes, sir. It was okay. No problem, sir.
okay. Okay. All right.
Okay.
So shall I start?
So, yes, sir. So, as there are no more questions, I would like to thank the doctor. I would like to thank the Dr. Rachayya Arakerimath for delivering such a nice session, and I hope all the students must be benefited by his vast experience and this very nice delivery of the topic. And I hope the students will think about this topic for the further research purpose, and they will get good knowledge out of it. So thank you, sir, for the nice delivery of the session, and thank you all to all participants for having attending this session. Thank you all.
Thank you, sir. Thanks a lot, sir. Okay. Okay. Thank you, sir. We will meet.
Yes. So everyone can leave the meeting. Thank you.
Thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.
Thank you, sir.